Good evening, and welcome to another lovely session of CENG 3325 Structural Analysis. Alright, so today I want to look at a application of the force method to derive equations for deflection of beams. And this is going to be the 25th lecture in our video series. And like I already said, we are going to look at applying the force method to beam deflection equations. So our video today is going to be a bit on the long side, so you might want to get a snack if you are so inclined. So, for this particular problem, we are not given anything. Rather, we are asked to find the following. Let's go ahead and close that. Let us find the following. Find the equation for the deflection of a fixed beam, of length L with a uniform load across it. Of length L with a uniform load W across it. Or I suppose I could say uniform distributed load. Uniform distributed load L or W across it. Load W across it. Okay, so drawing this out, let me illustrate what I want us to find. So I have, what I really want to look at is, I want to look at a continuous beam, or sorry, not a continuous beam, a fixed beam here. And if I have a fixed beam here, this is one of our classic cases of beam bending. Well, if I can manage to not erase my beam, that would be good. Like so here. And so we have a simple beam, not a simply supported beam, but a fixed beam, a fixed support on the left-hand side and a fixed support on the right-hand side, and a uniform distributed load W across the top. A uniform distributed load W across the top of the beam. W here. Then I'm going to call these ends A and end B, or end A and end B. So nothing too earth-shattering here. And let's see, from basic static equilibrium, if I do a balance of forces in the vertical direction, it's very easy to see that on the left-hand side, I will have a vertical reaction of WL over 2, and the same on the right-hand side. And I can get this just by arguments of symmetry. WL over 2 here. So I have a uniform load, W across the top of the beam, and that would be in kips per foot, or pounds per foot, or pounds per inch, or newtons per meter, or whatever this might be. But then I would also have some sort of moments on the left and right-hand sides. So I would have, again, because these are fixed supports, let's say I have an MA here, and an MB. An MA and an MB. Now, this is one particular problem that, unlike the previous examples I've worked through with the force method, I am not going to be solving for a particular number. This particular problem, I'm going to illustrate how you can use the force method to actually derive equations of deflection for beams. So, and this is also a very interesting problem in that I already know the answer that I'm aiming for beforehand, so we'll actually have a way of checking our work as we go. Or maybe not as we go, but at least for our final answer. So, again, like I said, this is one of our classic cases of beam bending, and when I went into the steel manual and took a look at this, when I looked in the steel manual or any other convenient beam table, I found an equation illustrating or describing this exact situation. And the delta max, which is going to be the deflection at midspan here, the deflection here. And the final answer that we need to get is WL to the fourth over 384 EI. 384 EI. So this is our ultimate goal. And our entire video today, our entire discussion today, is going to look at where do these equations come from. So we see these equations for bending in various places. We see them in, or equations for deflection, equations for bending, etc. And in cases like simply supported beams, it's very easy to, or in the case of statically determinate beams, it's very easy to derive those using the methods that we've looked at throughout the entire semester. But when we look at statically indeterminate systems like this fixed beam, then it can be a bit more challenging. And we need to use some method like the force method, the slope deflection method, sometimes virtual work, other methods, etc., in order to find an actual useful equation. So first of all, let's talk about this beam. This beam is going to be indeterminate to the second degree. I have 3 reactions on each side. I'm ignoring the x reaction on each side right now because there's clearly no x forces on the beam, so you can just go ahead and ignore that. And but then I do have a vertical reaction and a moment on either side. And I just decided to go ahead and assume that they were bending like this. Although they could be bending the other way, we'll find out. So I went ahead and just assumed they were bending like this, and or the moments were reacting like that, the reaction moments were like this, and if we get the opposite, or if we get a negative number on one of them or both of them, it will simply mean that our moments are opposite what we initially assumed. So there, again, when you're working with the force method, there's nothing wrong with assuming the wrong direction. So this is not the first video where we've looked at the force method, so I am going to use some concepts that we went through in the past couple of videos. So if you haven't taken a look at those, please do so, and that will hopefully get you more familiar with the topic of the force method. And because this is indeterminate to the second degree, I am going, and again, as a review, to determine degree of indeterminacy, I have 6 reactions, and I have let's see, I'm going to have 6 reaction forces, and, well, backing up, technically I might be able to argue this is indeterminate to the third degree, but I actually I took care of one of those by just assuming symmetry and saying, okay, this WL over 2 has to be equal to this WL over 2, so I'm going to be able to get away with just using simply using 2 secondary beams. So I already have my, these are basically already known, but what I don't know is this MA and MB. So I'm going to go for that. Now, truth be told, I could actually use symmetry as well here and say that this has to be symmetric to this, but I felt I'd go through and really work through it and show how they actually do end up equal and opposite. And the other reason I chose this is that for this particular beam, I will get to show you, or for this particular problem, I will get to show you how you can use the force method not just for unit loads, but for unit rotations or unit moments or unit couples. So let us begin. Again, this is going to be applying the method that we have looked at in the past couple lectures. So let us consider the primary beam. And this, of course, is the beam with the redundant forces removed, or the redundant reactions removed, and the real loads present. So looking at this, I decided that the simplest way to analyze this would be to remove the moments. So I'm going to remove the fixed support here and the fixed support here, and basically turn this into a pin-pin or a pin roller as I will analyze it. Now, technically it would be a pin-pin, but I'm just going to go ahead and analyze it as simply supported because, again, there's no horizontal loads on this, so that won't cause a problem. So primary beam, my primary beam is going to look like this. I'll have a distributed load W all the way across the beam. I'll have a distributed load W all the way across the beam. Then I'll have the same reactions, WL over 2. That's not going to change. And a WL over 2 on the right-hand side as well. Then this is going to have a length of L. Again, nothing new here. a beam length of L. And like I often do like to do, I am going to show my angles here, or my deflected shape, and then resulting angles. So my deflected shape is going to look like this. Ideally it would be drawn symmetric, but oh well. And then our angles, I'm going to have an angle here and an angle here, and this is end A and end B, and this one is going to be theta A naught, and I'm going to draw this or label this as a capital theta. So how I distinguish my capital from my lowercase thetas, usually my lowercase thetas look like this, and my capital thetas have a bar that doesn't go all the way across. So that's capital theta. So my capital theta, this will be capital theta A sub O. And that is the angle of rotation of the beam at point A with the real loads present, but without the redundant supports. And then I'll also have theta B naught, or theta BO, which is the same thing. Again, we tend to use capital letters, capital Greek letters for the real deformations. Theta B naught. Okay, and so I do want to actually get these, and the trick of this is that we'll have to actually derive them. So we are going to actually have to derive this, which will make things, a little bit interesting. So let's go ahead and do this. Conceptually, it's not too difficult, but it is quite a lot of plugging and chugging. So first of all, our load function, W of x, well, that's just W, a constant W across. Then V as a function of x, the shear, is going to be equal to the negative integral of W as a function of x dx, and that's just going to be equal to negative Wx plus C1. And, but I do have a boundary condition here, so we need to get that C1. And the boundary condition is that the shear V at x equals 0 is going to be equal to WL over 2. It's equal to WL over 2. So therefore, V as a function of x is equal to negative Wx plus WL over 2. Plus WL over 2. And now we have our shear function. Then m as a function of x, the moment as a function of x, is simply going to be equal to the integral of the shear function of x, shear as a function of x dx. And if I go ahead and take the integral of this, again, this is just straightforward polynomial integration. This is going to be equal to Wx squared over 2 plus WLx over 2. Just adding an x to our constant here, and then plus a C2. Now we need to have another boundary condition to get the C2, and that boundary condition will be, well, it's a pin support on the end now, so that means that on either end the moment must be 0. So the boundary condition is then that m at x equals 0 is equal to 0. And clearly that will lead to C2 also being equal to 0. And now I have a moment function for the primary beam that is simply negative Wx squared over 2 plus WLx over 2. WLx divided by 2. Okay, so we have that. Next we need to do, again, we're going to work all the way through this, and I next want to get the theta, the slope of the beam, as a function of x, and we're going to do that again by integration. So theta as a function of x is equal to, let's see, that is going to be equal to 1 over EI times the integral of m as a function of x dx, m as a function of x dx, and if you take the integral of the previous function, you will get 1 over EI times negative Wx to the third, negative Wx to the third over 6, plus WLx squared over 4. But of course, we cannot forget our trusty constant, so WLx squared over 4, and then plus C3, a constant 3. And unfortunately, we don't have anything we can immediately solve for that C3 with, because of the fact that we have basically a simply supported beam here, we don't know the angle, and so we're going to have to come back later and get that after the next level of integration. So y as a function of x, then the actual deflection as a function of x is going to be equal to the integral of theta as a function of x dx, and so that is, if I can pull out the 1 over ei, and I will have the integral of negative wx to the third divided by 6 plus WLX squared divided by 4 plus C3 dx plus C3 dx. And when you get that integral, you will get, when you take the integral of that, you'll have 1 over ei, again just integrating polynomials, 1 over ei times negative wx to the fourth, negative wx to the fourth divided by 24 plus WLX to the third divided by 12. Again, just the integration of this, very simple polynomial integration, nice friendly integration, Cal 1 stuff, kid stuff, plus C3x, and then plus C4. So we now have something that we do have a final deflection equation, well, actually nowhere close to a final deflection equation, but we've at least finished integrating for our primary beam, and we do apply a couple boundary conditions. And the first one, I can say one boundary condition, y at x equals 0 is going to be equal to 0, and when I plug in, because each of these terms here has an x, when I plug in 0 and 0 here, that C4 will clearly equal 0. So that constant drops away. And the next one I can apply is that is on the other end of the beam. Boundary condition, the deflection, the actual drop in height from at both this point here and this point here must both be equal to 0. And so not only is y at x equals 0 equal to L, not only is y at x equals 0 equal to 0, but y at x equals L is equal to 0. And so let's go ahead and substitute that in. And so I'll get 0 equals 1 over ei, 1 over ei times, let's see here, times our equation, negative w times L to the fourth divided by 24, plus WL times L to the third, divided by 12, plus C3 times L. And what I'm really after is this C3 here. So the 1 over ei goes away, and if you gather up all like terms, move them over to the other side, and solve for C3, you will find that C3 is equal to negative WL to the third over 24. C3 is negative WL to the third divided by 24. And then in turn, I have my full, I now have my full deflection equation for my primary beam. Y as a function of x will be equal to 1 over ei. 1 over ei times negative wx to the fourth divided by 24 plus WL x to the third over 12, and then minus our constant, minus WL to the third over 24x. But what I really want, though, that's nice and all, what I really want is this theta expression, because I'm going to apply the force method here using a balance of rotations rather than a balance of deflections. So what I really need is my theta of x function, and that's really not too bad. All I got to do is plug the C3 into this up here. So C3 then, theta as a function of x, theta as a function of x is going to be equal to 1 over ei times, again, all I'm doing in this step is putting my constant in to get my final theta of x function for the primary beam, negative wx to the third over 6 plus, plus WLX squared over 4 and minus WL to the third over 24. WL to the third divided by 24 over 24. So negative WX to the third over 6 plus WLX squared over 4 minus WL to the third over 24. And I need to get two different things. First, I need to get the theta at x equals 0, and next I need to get the theta at x equals L. So the theta at x equals 0, or just theta of 0, is going to be, well, that's clearly just going to be, if I put in 0 here, if I put in 0 for x, this goes away and this goes away, and I will get negative WL to the third over 24 EI. Negative WL to the third over 24 EI, and this is going to be my theta A naught, my capital theta A naught. This is the rotation at joint A with the actual loading applied if the redundant reactions were removed, and the redundant reactions that I chose were my moment supports, or my moments. So this is my capital theta A naught. Again, that is the rotation at A if the moments were removed, or if the fixed supports are removed. Then theta at x equals L. If I go ahead and plug in L for this equation and simplify, let's just go ahead and show what this would look like. That would be 1 over EI times negative WL to the third over 6 plus WL times L squared over 4 minus WL to the third over 24. So then simplify and collapse this down. If you simplify and collapse this down, you will find that this theta is then equal to WL to the third divided by 24 EI. Divided by 24 EI. And this is equal to capital theta B naught. That is, of course, our again, our real deformation, or our real rotation at joint B from on the primary beam, or in other words, that is the rotation that joint B would experience if the redundant reactions, or our fixed reactions in this case, were removed. And notice these are actually equal and opposite, and they do actually correspond to, that is also interesting. Notice that A naught was negative and B naught was positive, and that makes sense when you consider our standard directions of rotation. I would expect this one to be positive and this one to be negative. Clockwise, counterclockwise, etc. Okay, and so now we have finished analyzing our primary beam, and the next thing we need to do is to analyze our secondary beams. And we're going to need to use two secondary beams because we have two redundant forces that we removed. So let's analyze our secondary beam, or secondary beams. And if you recall from our previous work, to analyze the secondary beam, we use the same exact geometry, except we remove the real loadings and we apply a unit load or moment at the location and in the direction that of the assumed thing that we removed, or the assumed reaction that we removed, just basically apply a unit load or moment at the location and in the assumed direction of the restraint that we removed. So analyze secondary beams. Now I'll analyze the secondary beams. And here, let's consider this. So let's say we have our simply supported beam again. Nice, friendly, simply supported beams. And the first one I'm going to work through is one with one where we deal with the moment from A, or the moment at A, or the reaction MA here. And since I assumed this was going clockwise, I'm going to do the same thing for my one kip, my unit moment here. So this wouldn't actually be a kip. This would be something like a kip foot, a kip inch, etc. But because I'm not doing this in terms of units, I'm doing this unitless, I'm just going to put the number 1 here instead. So whatever unit system you'd have, that would be what you're using. There would be some sort of unit there if you're doing this with numbers. But because I'm doing this as a derivation, I want to literally just put unity there, just the number 1. Then I'm going to have an AY here and a BY here. AY and BY have to balance each other out, have to be equal and opposite, but they still must come together and form a couple to balance out this one unit couple here. You see that unit moment there. And there is, of course, no distributed load because we're, again, for our secondary beams, we have removed the real loads. Then, let me go ahead and show the deflected shape, and then highlight the deflections of interest, or in this case, the rotations of interest. So just like in the other case, just like in the case of the primary beam, we're going to be looking at the rotations on either end of the beam. And this particular rotation is going to be theta AA. Lowercase theta AA here, because again, this is a rotation from a virtual load. That's why I tend to use the lowercase. So this is theta AA there, if you're having trouble reading my handwriting, or theta sub AA. That is the rotation at A caused by a unit load at A. And then we also have theta BB, or sorry, not theta BB, theta BA, which is the rotation at B from a unit load at A. If you can recall the naming convention we developed over the last couple of videos, AA refers to the first subscript refers to the point that you're looking at the deflection, or the rotation in this case, and the second one refers to the source of that. So theta AA is the rotation at A due to a unit load at A, or a unit couple at A, and theta BA is the rotation at B due to a unit couple at A, theta BA. Okay, so I first need to get my reactions, which you can probably hopefully figure out in your head, but if not, that's fine. Let me just go ahead and do a balance of moments. A balance of moments about A. I would have BY, or actually negative BY. Negative BY, actually I think I drew those in the wrong direction, sorry about that. That doesn't make sense for them to be going that way. They need to be acting in the rotational direction opposite my assumed couple, or my unit couple there. So that works out a little better. So balancing moments then. Negative BY, or actually positive BY, because now that we got that fixed, BY times L, I've been using capital L, is going to equal, or minus 1 is equal to 0, which means that BY is equal to 1 over L. Then I can do a sum of forces in the vertical direction and clearly see that AY is also equal to 1 over L. The only difference is that BY will point upward while AY will point downward. They will have the same magnitude, however. And so now my beam, beam with all of its reactions here, with all of its reactions present, will collapse to this. Let's show the loads on here that I'm going to use to find the shear, moment, deflection, etc. I have my units load here, my unit couple. Then I have a downward reaction here of 1 over L, and an upward force here, an upward reaction of 1 over L as well. 1 over L as well. So then I can start working through the equations of deflection, or the equations of shear and bending and all that good stuff. So W is a function of x. Well, there is no distributed load on this, so W is a function of x is just equal to 0. And if you remember shear and bending moment diagrams, the shear diagram for this is obviously just going to sort of start down at negative 1 over L, remain constant, and then jump back up to 1 over L on the right. So V of x will just be equal to a constant value of negative 1 over L. Don't even need to get don't need to worry about finding a boundary condition for that, because we already have the whole thing. Then M is a function of x. is going to be equal to the integral of v of x dx, which will be equal to just the polynomial integral of that with respect to x, negative 1 over L x plus c1. And I will need a boundary condition for this. And that boundary condition can simply be, well, it is a simply supported beam, and so m at x equals 0 is going to be equal to 0. M at x equals 0 is equal to 0, so that leads us to c1 also being equal to 0. So no great trouble here. Oh, actually no. Sorry about that. That is not correct. The moment at A is not 0. It is actually going to be equal to 1. Because the moment diagram is not going to start off at 0. It's only 0 on a pin support if there is no couple present on the left-hand side or at the location of that. So I know that the moment at x equals 0 is not 0, but because we have this unit couple here, well, it's a unit couple applied in the negative direction, so internally this is going to cause a positive jump in the moment, the bending moment inside the beam, equal and opposite forces, and all that. So m at x equals 0 is actually equal to 1, so if I were to plug this in, I would get that c1 is going to equal to 1. So m as a function of x then is going to be equal to negative x over L plus 1. When was the last time you saw just a very simple plus 1 in an equation? Doesn't happen that often, that's for sure. So negative x over L plus 1. Then theta as a function of x is going to be equal to 1 over ei times the integral of theta, or times the integral of m as a function of x dx. So that is the integral that is 1 over ei times the integral of negative x over L plus 1 dx. And that's just going to get the integral, or the result of that is going to be 1 over ei times negative x squared divided by 2L plus x plus a c2, another constant. And just like in the previous case, we're not going to be able to immediately get this constant 2 here, because we don't, of course, know anything about the rotation at ends A and B, at least not yet. So we're going to have to go through the next level of integration, just like we did previously. And then y as a function of x is equal to the integral of theta as a function of x dx. And working through that integral, let's see, that's going to be, if you go and plug and chug through that integral, you will get 1 over ei. And this one isn't really even that plug and this one would be hard to even describe as plug and chug, because it's really not too bad. X to the third over 6L plus x squared over 2 plus c2 x plus c3, c2x plus c3. And I can use the exact same boundary conditions I used last time, although it will produce different values. Boundary condition, or at least the second one will. Boundary condition, I do know that y at x equals 0 is going to be equal to 0, even though there is a moment, even though the moment may not be equal to 0 there, the deflection at x equals 0 is equal to 0. So I know that's the case. And because all of these terms have an x in them except c3, that leads us to that c3 is equal to 0. Then if I put in, then I also know another boundary condition, y at x equals L is equal to 0, so same kind of thing. So if I put in 0 for y of x is equal to 1 over ei times negative L to the third divided by 6L plus L squared over 2 plus c2 times L plus c2 times L here. And if you go ahead and solve for c2, you'll find that c2 is equal to, and again this 1 over ei just goes away, you will find that C2 is equal to negative L over 3. C2 is equal to negative L over 3. And I could go ahead and list out the y as a function of x equation. Well, I suppose I could, why not? Y as a function of x for our first primary beam will then be 1 over EI times negative x to the third divided by 6L plus x squared over 2 minus L over 3. Or sorry, minus, no, actually, sorry, that is fine. Minus L over 3 here. Minus L over 3. And then, let's see here. Oh, L over 3. Let me double check. Oh, yeah, something didn't look right. L over 3 times x. There we go. That looks a little better. Okay, that makes me much happier. And yes, so that's good. We have our C2. Okay, I just want to make sure we're not missing anything in our equations. Okay, in fact, I'm going to correct my notes a little bit. My notes here are missing a x there, but we found it. All good. Okay, so next I want to work through, I want to list the deflection equation, or the rotation equation. Taking this rotation equation here, theta as a function of x is going to be equal to 1 over EI times negative x squared divided by 2L, negative x squared divided by 2L plus x, and then our C2, which is the negative L over 3, minus L over 3. So now, for our first secondary beam, we have our an expression or an equation to find the slope of the beam at any point x. And then I can go get my theta AA and my theta BA. I am gonna try to squeeze this on here. Theta AA, the rotation at A caused by the unit load at A, or the unit couple at A. This is just going to be equal to theta at x equals 0. And if you plug 0 into this, well, you will get that this is equal to negative L over 3 EI. Negative L over 3 EI. And then theta BA, this is equal to theta. This is the rotation on the right-hand side of the first first secondary beam. Yeah, the first secondary beam. And so this is theta at x equals L. And just plugging L into this expression, if you go ahead and do that, if you plug L into this and solve and get common denominators and solve for a final value of theta, you will find that this is equal to L over 6 EI. Positive L over 6 EI. So on the left-hand side of the beam, you'll have negative L over 3 EI. On the right-hand side of the beam, you'll have positive L over 6 EI. And if you look at the beam, this does make sense. This is where the couple is applied, so I would expect a larger rotation there, because this is not a symmetric system when we have a couple on only one end of the beam. And this is a much smaller, this is actually half the deflection, and the directions are in what we would expect for our rotations, or for our deflected shape. Okay, so we have our two, thetas for the load at A. So next I need to work through my second secondary beam, which is always a weird thing to roll off your tongue. Analyze second secondary beam. And this one's going to be just like the other one, except reversed. So I'm going to go ahead and just give us the reactions, because again, that's going to be fairly trivial to solve, just like we did previously. And the only difference between these two beams is that this one's going to have the unit couple on the right-hand side. So a unit couple of 1, or a couple of 1 on the right-hand side. And then the reactions are going to be the same magnitudes, but in the opposite directions as the previous one. So 1 over L, and then 1 over L like this, and the beam has length L. And the beam itself has length L. Then let me go ahead and show the deflected shape just like I did previously. So the deflected shape looks something like this. Again, if I can manage to draw a straight line, well, a continuously curved line in this case. Good enough. And what I really want to do is provide the labels for the rotations. So this here is going to be theta AB. Theta AB, that is the rotation at A caused by a unit load at B. And then, of course, we have here theta BB, that is the rotation at B caused by a unit couple at B. So now this is going to be very similar to the previous one. So I'll try to move through this fairly quickly. First of all, I can directly get the shear. We have no distributed load like last time, or just like last time we had no, for the last secondary beam, we had no distributed load. So V of x here is just going to be equal to positive 1 over L. Previously, it was negative 1 over L, but here the reaction on the left-hand side is going to cause us to jump up to 1 over L, and it's going to remain constant all the way across before dropping back down. So V of x equals 1 over L, and then m of x is just going to be the integral of that, and the integral of that, of course, dx, and the integral of that is going to be very similar to last time, x over L plus c1, and I do need a boundary condition. And in this case, I can actually say that the moment at 0 is 0, and that's because there is a pin there, but there's no couple there. So I can just say that m at x equals 0 is equal to 0, and that leads us to c1 being equal to 0. So that means that m as a function of x is nothing more than simply what will that be? That will just be x over L. Then I can get theta as a function of x. That is, of course, 1 over ei times the integral of m of x dx, which is equal to 1 over ei times the integral of x over L dx, and that integral then comes to, let's see, 1 over ei times x squared over 2L plus c2. X squared divided by 2L plus a second constant c2. And just like in the previous case, we're not going to be able to directly solve for the constant that comes from the theta function just right yet, but we'll come back to it. And then y as a function of x is equal to the integral of theta as a function of x dx. And if you go ahead and take the integral of that, you'll have 1 over ei times, let's see, the integral of this, and that will come to, let's see what I have in my notes. Okay, that's good. X to the third divided by 6L, x to the third divided by 6L, plus c2x plus c3, plus c2x plus c3. And a boundary condition, well, the first one I can do is I can use to knock out c3 very easily. The boundary condition is just like, and we're going to use the exact same boundary conditions as in the two previous beams, so you may start noticing some patterns here. Boundary condition, y at x equals 0, what do you know, that's equal to 0, which, what do you know, leads to c3 being equal to 0. And boundary condition, y at x equals L is also equal to 0. And if you go ahead and apply that, if you put in 0 for y and L in for x, and then without this term here, and then solve for c2, you will find that c2 is equal to negative L over 6. It's equal to negative L over 6. So our y as a function of x expression then let's see, so negative L over 6, and so once we have that, the negative L over 6, we can put it back into our theta as a function of x expression here, x squared over 2L, and then minus L over 6. So again, theta as a function of x then is just going to be equal to 1 over EI. 1 over EI times, let's see, that is x squared divided by 2L minus L over 6. Minus L over 6 here. So x squared divided by 2L minus L over 6. And now I'll actually get the points, or the rotation at the points I'm interested in, or the rotation at the points where I'm interested in. And theta AB, well, theta AB, again, the rotation at A from the force at point B, or the couple at point B, this is, for this beam, is just going to be equal to the theta at 0. And that's just going to come to, this term will go away, and I will end up with L over 6EI. Or, actually, yes, L over 6EI. Negative L over 6EI. Negative L over 6EI. So negative L over 6EI. And then theta BB. Theta BB here, this is going to be equal to theta at L, and this is going to then be equal to, if you go ahead and plug this into this and simplify and solve it, you will find this is equal to L over 3EI. So let me go ahead and create a summary table of my deflections, or my rotations, I suppose. So summary of rotations. Summary of rotations. So a summary of my rotations, let's see. I'm going to split this up into point A and point B. Point A and point B. Well, let's get the real deformations here again from the primaries. Theta A naught and theta B naught. Capital theta, theta B naught. This is going to be, or we calculated this as negative WL to the third divided by 24EI. And we calculated this one as the opposite. So WL to the third, positive WL to the third over 24EI. Then, let's see the rotations, again using lowercase theta from our virtual loads. Theta AA came to negative L over 3EI, and theta BB, this one came to L, positive L over 3EI. Positive L over 3EI, and theta AB came to negative L over 6EI, and theta BA came to positive L over 6EI. So you notice that wherever the, for the case of these simply supported beams anyway, wherever a couple was applied, we end up with a larger magnitude rotation than in the case where it was on the opposite end of the beam, which that really isn't that surprising. But also look here, all of my rotations for the left end of the beam were negative, and all the rotations for the right end of the beam were positive. And that won't be true in all cases, but just because of the directions of things I assumed, the directions of the moments I assumed and deflections, etc., they all ended up lined up like this. But because it should not surprise us that we get this kind of symmetry going on, because fundamentally this is a symmetric system. And I probably could have used that to eliminate one of my secondary beams. I probably could have gotten away with one secondary beam in this problem, but I did want to show how to work with rotations when you had two secondary beams. So the next step is going to be to balance the deformations. If you remember from the force method, the theory of the force method, basically what we're sort of saying is we're saying, okay, well, let's say I remove these redundant forces. In this case, the redundant moments at the start of the beam. If I remove this moment here and here, how much is this thing going to bend? And then I'm going to say, okay, well, I want to find how much moment it takes to bend that thing back up to put it back where it was. And I'm going to do that by finding how much a unit load or a unit moment here causes it to bend. And then I'm going to apply a balance of rotations, mathematical balance of rotations, to find that value. So for rotation of point A, if I look at the rotation of point A, or first let's consider the rotation of point A. Well, I can say that capital theta, this is a full real deformation, not a unit one, or not one from a unit, plus MA. Again, we said that the theta AA, for example, it's a lowercase theta. This is the rotation caused by a moment of 1 at joint A. But odds are I might have something far larger than that. If this moment was 20, then it would cause 20 times the amount of rotation as the unit couple that we calculated theta AA with. So we're going to multiply this by this to get what the real deformation that reaction produces. Then plus MB times theta AB. Again here, that is the rotation at A caused by the moment at B, and that then just goes to 0. Now I want to put in the known quantities. Negative WL to the third divided by 24 EI plus MA times that is going to be negative L over 3 EI, negative L over 3 EI plus MB times negative L to the third, or not L to the third, sorry, negative L over 6 EI. Now if you go ahead and cancel out like terms, if you go ahead and I'll call this, of course, all this is equal to 0. If you get rid of the negative, combine like terms, cancel things out, etc., you will find that, and then I also went and solved for MA, and when I did that, I found that MA is equal to negative MB over 2 minus WL squared over 8. So I'm not able to get the actual MB or MA yet, but I do now have MA in terms of MB. And again, all I did was take this and isolate MA by itself and simplify. Then let us consider the rotation at point B. Rotation at point B. The rotation at point B, let's see, capital theta B naught plus MB times theta AB. Again, this is the rotation at A caused by moment B, or the reaction at B, and we just have MB there. Plus, let's see, that's going to be MA times theta BA. The rotation at B caused by the moment A. All this is equal to 0. Then plugging in known quantities. Well, let's see here. Let's go ahead and put in our quantities for the thetas, both real and the units. So WL to the third divided by 24 EI plus MB times, then that's going to be 3 or L over 3 EI plus MA times L over 6 EI over 6 EI. All this equals to 0. And then here, then I want to go and simplify this a bit. If you simplify this a bit, you will get WL squared, canceling out a few terms. WL squared over 8 plus MB plus 1/2 MA. A lot of this stuff cancels out. 1/2 MA. And at this point, I'm going to take my expression for MA here and substitute in here. So WL squared divided by 8 plus MB plus 1/2 times negative MB over 2 minus WL squared over 8. Minus WL squared over 8, and all of this is equal to 0. And let's see here, so let me double check this. WL squared over 8 plus MB plus 1/2 of negative MB over 2 minus WL squared over 8. Yep, we're good there. And if you gather all this up, if you work through a whole bunch of messy algebra and solve for MB, you will find that MB is equal to negative WL squared over 12. Negative WL squared divided by 12 is the final form of the moment at B. So I now actually know a proper reaction. I know that MB is equal to negative WL squared over 12. And if you take that, feed it into here, combine these together, you can also get MA, and you will find that MA is equal to, let's see here, also negative WL squared over 12. It's almost like this is a symmetric beam. So I could have used arguments from symmetry, but I didn't, and I actually algebraically verified. Now, when I did this myself and earlier on my notes, working this out by hand, I did actually work through all the algebra, but I'm trying to, this problem is long enough, so I thought I'd simplify the algebra or skip a few steps on the algebra. I think by this point, algebra shouldn't scare you at all. At least I hope so by the time you're in a structural analysis class. So now, notice, we have MA and MB as negative. That does not mean they are clockwise. That absolutely does not mean they are counterclockwise. What it means is that I assumed wrong. I assumed that MA was going this way, and so I guess that would be negative in that case, negative direction, and I assumed MB was going this way. What it really means was I was just really bad at assuming things. And so it turns out that MA is actually going counterclockwise and MB is actually going clockwise. So next I'm going to finish up the problem by going for the final desired quantity, which is the deflection at the midspan of the beam. And I'm going to do this by analyzing the now statically determinate beam. So let us next analyze the now statically determinate beam. And I'm going to go ahead and draw this out. The now statically determinate beam. So what was once a very annoying problem now isn't too bad. And I could draw this as a fixed beam, but actually I can just go ahead and draw this as a simply supported beam. I can continue drawing it like that if I want. And so I have this is effectively a simply supported beam now, with the following loads on it. Here. Let's see. Well, let's just say let's trust but verify and see if we can actually confirm which direction AY and BY will be in, because we are putting the redundant reactions back on. AY and BY. And I have moments of WL squared over 12, just like we got previously, WL squared over 12, WL squared over 12 here, and WL squared over 12 here. And this is, of course, a beam of length L. Oh, and of course, I almost forgot my actual loading. We can't forget that. My distributed load of W, that still hasn't gone away. We're back to a real beam that is statically determinate. And once we have, and again, as we've known from previous discussions, once you know the end forces in a beam, you can find pretty much anything that you would like about it. It's once you know the end forces, the rest is cake. Well, cake-ish. So if you go ahead and do a sum of moments, about point A, let's go ahead and solve for the reactions. Let's say you would have WL squared over 12 and minus WL squared over 12. And what do you know, those two things cancel out. And then let's see, minus WL, the equivalent point load of this thing, times its moment arm length of L over 2, plus L times BY equal to 0. And what do you know, BY is equal to the exact same WL over 2. And in turn, if you do a sum of forces in the y direction, you can clearly see that AY is also equal to WL over 2. So again, nothing terribly earth-shattering there. We now have our reactions. And so I want to work through one last layer of this messy four-stage integration. So W of x is again just going to be equal to W. V of x is again going to be equal to the negative integral of W of x dx. So this is definitely going to be very similar to our first set of integrals, except we'll have some different boundary conditions. Well, except for our shear here, that's going to be exactly the same. If you do this, you will get, let's see, that was negative Wx plus a C1. But of course, we know from boundary conditions, like we did previously, that V at x equals 0 is equal to our WL over 2. That should be a little cleaner. 0 is equal to WL over 2. And so then we now know that V as a function of x for this beam, V as a function of x is equal to negative Wx plus WL over 2. Plus WL over 2. Now, when I want to talk about moment, as we recall from statics and mechanics and other courses, we know that if we have a counterclockwise moment, or a point moment, or a moment applied at a certain point, because this is a positive external moment, internally it's going to cause a downward jump in moment. So our moment diagram for this beam is actually going to start negative. So when we get to our moment integration, we'll have a negative boundary condition there. Okay, so moment, m as a function of x, is going to be equal to, that's the integral of v as a function of x dx, and that will come to, let's see, that is negative wx squared. Negative wx squared over 2 plus wlx plus wlx over 2 plus c2. Plus c2 here. And boundary condition. Now the interesting boundary condition here, again, is not that I cannot say that just like in the case where we had a couple on the end, I cannot say that the moment on the left hand of the side of the beam is 0, because even though I'm modeling this as a pin support, I have a couple applied at the end of that. So the boundary condition here actually is that m at x equals 0 is equal to the opposite of whatever this thing is. So that would be not positive, but negative WL squared over 12. Again, is equal to negative WL squared divided by 12. So plugging 0 into this and this over here for our moment, we clearly see that C2 is just going to be equal to negative WL squared divided by 12. So then, so then m as a function of x, if I were to write this all in one line, is negative WX squared divided by 2 plus WLX over 2 minus WL squared divided by 12, minus WL squared divided by 12. Then I want to get theta as a function of x. This is equal to 1 over EI times the integral of m as a function of x dx, m as a function of x dx, and working through that integral, that's going to be 1 over EI. Let me write on another line in case I need a little more room. 1 over EI times negative WX to the third divided by 6 plus WLX squared over 4, WLX squared over 4, and then minus WLX squared, or WL squared over 12 times x, plus a constant C3. And just like the 3 other times we've done this, we're not going to be able to initially get that. So we'll keep going. Y is a function of x is equal to the integral of the rotation, or the slope, theta of x dx. And you go ahead and take the integral of that with respect to x. You will get 1 over EI, 1 over EI times negative, if I can keep from jumping ahead, negative WX to the fourth divided by 24. This turns into over 24, plus WLX to the third divided by 12 minus WL squared x squared divided by 24, WL squared x squared over 24 plus C3x plus C4. Now the first boundary condition I can use is, because this is being modeled as a simply supported beam, y at x equals 0, of course, is going to be equal to 0. So that leads us to C4 being equal to 0. So we know C4 is equal to 0. Then another boundary condition, maybe I'll work through this on the next slide. Boundary condition, y at x equals L is also equal to 0. So if I set this up, y as a function of x equals 1 over EI. This one is quite involved, so I'm going to go ahead and do that. Just want to write this out. 1 over EI times negative W x to the fourth divided by 24 plus WL x to the third over 12, WL x to the third over 12 minus WL squared x squared divided by 24, and then plus C3x, and then 0 equals 1 over EI, 1 over EI times, let's just go, let me go ahead and substitute this in, negative WL to the fourth divided by 24 plus W, that's L times L to the third, well, L to the third over 12 minus WL squared L squared over 24 plus C3 times L. And here, let's take a look at this then. Let's see. Looking at this. Now, look what we have here. Let's see. First of all, the EI can just go away. The EI just goes away. And, interestingly enough, let's keep working through this. This will, I'll have a negative WL to the fourth over 24 plus WL to the fourth over 12 minus WL to the fourth over 24 plus C3L, and this equals 0. Now, take a look at this. This, if I get rid of over 12, if I just do a factor, if I put a 24 there, I could put a 2 here. So if now these are all in 24ths, 2 minus 1 minus 1, 2 24ths minus 1 and minus 1 24th, all this stuff just goes away. So 0 equals C3L, and therefore C3 is equal to 0. And so then, so C3 is just going to be equal to 0. So that one's not too bad. So C3 is equal to 0. That just goes away in a proof of logic. And then I have a final deflected equation, a final deflection equation. No more integrals, I promise. Y as a function of x is equal to 1 over EI times negative WX to the 4th over 24 over 24 plus WL x to the 3rd x to the 3rd divided by 12 minus WL squared x squared over 24. So this is not my final answer, but this is still something pretty useful. What this is the deflection not at the middle point of the beam, but at any point in the beam. This is the deflection, the final deflection for any point in a fixed beam. At any point on a fixed beam. So I was specifically asked for the midspan deflection, and that would be the largest one, which is what we're often worried about. But if I know E, if I know I, if I know the overall length of the beam L, and I know the coordinate X, I can find, and again, well, fixed beam with continuous load, of course. With a continuous load, of course. Or continuous constant load. Anyway, continuous distributed load. So this is our final equation, or not our initially our final equation, but our total equation listing the overall deflection at any point x. So finally, let's go ahead and apply this. Find deflection at midspan, finally. This is the last step at last. And really, this is just plugging in a constant. So I'm going to plug L over 2 into this expression in for x, because that is halfway across the beam. Y at L over 2 is equal to 1 over EI times negative W times L over 2 to the 4th power divided by 24 plus WL times L over 2 quantity to the 3rd divided by 12 minus WL squared times L over 2 quantity squared divided by 24. Divided by 24 here. And let's go ahead and simplify this. 1 over EI, make sure we can get that final value that we've been hunting after for, quite a while. And so I'm going to go ahead and expand this and get negative W. Well, the numerator of this one will be L to the 4th, and the denominator will go down here. That will be 16 times 24. And then plus W. Let's see, that's going to be L to the 4th as well. And then 2 to the 3rd is 8. 8 times 12 minus W. L squared times L squared, L to the 4th again. But then we'll get a 4 in the denominator. 4 times 24. There. And this then is 1 over EI times negative. Let's just go ahead and leave that at L to the 4th over 16 times 24 for now. But looky here. This is L to the 4th. 8 times 12 is 96. and WL to the fourth, 4 times 12 is also 96. So that goes away. And 1 over EI, we're left with 1 over EI times negative here. And, oh, look at this. What does 16 times 24 come to? Well, if I throw that into my calculator, lo and behold, I get 384. And so I get a final value of Y max is equal to negative WL to the fourth over 384 EI. Now, the only question then is where the negative comes from, or what happens to the negative. In that equation that I got from the steel manual, they were defining downward deflection as positive. This one would be defined, this notation here just that I've been using describes downward deflection as negative. So that's the only source of the disconnect there. But we have seen where this equation comes from, and we have derived it using the method of using the force method, and also plenty of deflection via integration. So I do realize this is quite involved. I'm not going to regularly ask you to do this on, for example, I would not ask you to run through a derivation like this on an exam. That would take, well, definitely a lot longer time than we have on most exams. But it is useful to know where these sort of things come from. I do want you to appreciate what a powerful tool the force method really is. I did this for a fixed uniform beam, but you could do this for almost any type of loading. I did this for a beam like this, with a very simple, a nice symmetric beam with a fixed on either end. But if I wanted to, I could solve for equations for deflection for almost any type of beam. I could solve for the equation of deflection on a fixed pin, a fixed roller, a pin, a bunch of. I could have a fixed here, and a roller in the middle if I wanted to. The force method really is truly a very versatile and very powerful tool. But of course, the more redundancy you have, the more complex it will be. And just like here, if this hadn't been symmetric, then my vertical reactions wouldn't be symmetric, so I would need three. I would need to have had three redundant equations, and I would have needed to invert a 3x3 matrix to solve it. So, for example, instead of having a WL over 2 here, what if I had instead of having like a constant W, what if I had a linearly decreasing load? Well, in that case, symmetry goes right out the window, and we would have to solve everything for 3 levels of redundancy. That means 3 redundant beams. That means you would have maybe an ABC, and you'd have like theta AB, or you'd have like a theta AA, a theta AB, a theta AC, all down the line. You'd end up having 9 lowercase thetas, and you'd have to run a whole bunch of balancing, and it would be all sorts of fun. Anyway, I hope you have learned a bit here. I know this was quite long. I've lost track of time a bit, not sure what time it is exactly, but this definitely took quite a bit of time to work through. So again, this isn't necessarily something you'll want to work through all the time, and this is not something you want to do for every problem, but this kind of thing is how the kinds of equations you see in a beam table are derived. So it does take quite a bit, and again, this is for a relatively simple beam. This is for a uniformly distributed load fixed on both ends. It is statically indeterminate, but as you can see, it's not that complicated of a statically indeterminate beam. There are certainly more complex things out there. But if you want to work through one of these, go ahead and challenge yourself to. Now, if you want to challenge your own abilities, if you want to give this a try, I would suggest going to one of the beam tables and picking a formula and seeing if you can derive it. And I will admit, this is one of those things that you do have to check and recheck and double check and triple check your work, because look at this. I mean, we ran through 4 different beams essentially. We ran through first the primary beam, then 2 different secondary beams, and we ran through 4 levels of integration for each of those. And then when we finally got once we had the final beam as statically determinate, We then ran through the equations of deflection by integration one more time. So to get this, we had to run through 16 different steps of integration. So hopefully this gives you some appreciation for what is truly baked into the formulas that you see in the beam deflection tables. So if you want to give yourself a challenge, instead of just applying the formulas, go ahead and start deriving some of them and see if you are up to the mathematical and challenge, and see if you really understand the force method. So that'll do it for today. Hope you've all found this a bit enlightening. Hope you've all enjoyed this a bit. Hope you've all learned a few things, and thank you for bearing with me through this exceptionally long derivation and lecture tonight. Hope you've all enjoyed it. Hope you've all learned a few things again. And as always, thank you.